this lecture because we're going to start off with a group activity. I try to do a lot of group activities here in the classroom. It really helps nurture a sense of a community of learning in the classroom. It gets you to know each other much better, and you'll find that, hey, I'm not the only one who's having trouble with this concept. Or maybe you do understand it, but you'll practice that by explaining it to your partner. So let's start with this one today. Now, you don't know what these things are. Well, they're labeled for you. Here's a bunch of molecules. And maybe one of them is an atom, right? Which one's an atom? Helium, A, right? Okay, that was an easy one. Let's ask some questions here. Let me give you two of them. Let's do two things real quick. Just by letter, let's see if you know what hydrocarbons are and which two are structural isomers. Now, you don't have to do this by yourself. Go ahead and talk to your neighbors and see if you can identify of these 9 things. Which are hydrocarbons and which two are structural isomers? Discuss. All right, let's see if we have any consensus here. Who thinks they know about the hydrocarbons? Which ones are hydrocarbons? Who thinks they know for sure? Who has conviction? Nobody's certain. What do you think hydrocarbon means? Hydrocarbon. It has hydrogen and it has carbon in it, and that's it. Okay, so hydrocarbons, that would be C, ethane, and D, octane, and F, hexadecane. Are there any others? Now, of course, I haven't told you anything about like colors or whatnot, but you have the names here, like carbon tetrachloride, right? These are not hydrogens. They happen to be a different color. You may remember from Gen Chem 1 that our models, remember, models are just a way for us to envision what we really can't see on a molecular level. So we use things that are commonplace for us, like balls and sticks and colors. So black is usually for carbon. Yellow or white is usually for hydrogen. Red, what's red going to be? Oxygen. Red's for oxygen. So like this thing here, ethylene glycol, all right? This has hydrogen and carbon and oxygen in it. So this is what we call, anyone know? I know you haven't had organic chemistry yet, but oxyhydrocarbon, that's a good guess. But we actually call them carbohydrates. I know, kind of hydrates. It has carbon, hydrogen, and oxygen in them because it's a hydrate. Okay, how about the structural isomers? Which two are structural isomers? To get this one right, you have to know what a structural isomer is. I mean, what does that term mean to you? Anyone have an idea? So that's very, very close. So he said the structures are interchangeable. They can be switched around. That's essentially true. All right. The structure, I'm going to replace that word structure with the atoms. The atoms are the same, but their connectivity is different. Okay. So it's the same number of atoms. If we were to, well, now that I've said that, which two do you think are structural isomers? E and G are structural isomers. That's right. Because both of these have 2 carbons, C2. They each have 6 hydrogens and they have 1 oxygen. So C2H6O. So a structural isomer is something that has the same number of atoms. So the stoichiometry, there's that S word again. Stoichiometry is really important, okay? It's the molar ratio of things. It's the molar ratio of compounds in a chemical reaction, or it's the molar ratio of elements within a compound. And that's, in this case, it's 2 carbons for every 6 hydrogens for every 1 oxygen. But the connections are different, all right? These are different molecules. One is called ethanol and one is called dimethyl ether. One of these has a higher boiling point than the other. Any idea? Which one has the higher boiling point, ethanol or dimethyl ether? Go for it. Ethanol, because it has an OH bond, and you're talking about this bond right here. Any other guesses?
It's like it has symmetry.
Because it's symmetry. This is great. See, you guys are looking. What's different about this? This is symmetry. Now I need to know how to spell symmetry. I think that's right. Okay, so the answer to this question you'll be able to get when we're done with Chapter 6. See, that's the beauty of this slide. It reinforces what you should have remembered from last semester, Gen Chem 1, and also gives you a preview of the sorts of things that we're going to be learning about to allow you to answer this question. It turns out that this one here is the best solution so far from the ideas that you guys have set forth. It's not so much that this has an OH bond here, but it has more to do with the fact that on this molecule, this will undergo what we call hydrogen bonding. And hydrogen bonding is one of several intermolecular attractive forces that we'll be learning about in Chapter 6. These are the forces between molecules. Right? There's attractive forces between molecules. Last semester you learned about the attractive forces within molecules and formula units. Those are the covalent and the ionic bonds. Now we're going to be learning about the forces between them. All right? And the stronger those attractive forces are between molecules, the more energy it's going to take to get them to go from, say, the liquid phase into the gas phase. That's what happens when you're at the boiling point. In fact, boiling point is actually more complicated than that, but we won't get into that until chapter. So between those two then, even though they're the same ratio of elements, the connections are different, and that gives them different physical and chemical properties. Now, you have to remember the difference between a physical and a chemical property, but that's stuff from Gen Chem 1. So you will find that almost every lecture I'm going to say something that sounds similar to, and remember when you learn this in Gen Chem 1, all right? We really do put a huge emphasis on you knowing your stuff from Gen Chem 1. So I'm not going to be able to spend time reminding you about every single definition. But some of the important ones, yeah, we are going to be spending some time on. Okay, I'll be coming back to this slide when we get to it again later on. What you learned last semester was the intramolecular forces. This is within molecules. Those were the things like the covalent bonds and the ionic bonds. Those are going to be the strongest attractive forces that we'll be talking about. Ionic bonds are typically the strongest, but both ionic and covalent bonds are stronger than the intermolecular attractive forces. This is what we're going to be learning about now. These are the forces that are happening between the molecules. Right? These tend to be weaker. They also act over larger distances. These also will influence the physical properties of substances. Such as things I already mentioned, the boiling points, the freezing points, things like surface tension or vapor pressure, all sorts of physical properties. And even though I said I wouldn't define everything for you, I'll just remind you that a physical property is something that you can measure it in a substance, but the actual substance itself is not changing what it is. So for example, H2O that we mentioned. We've got solid H2O, liquid H2O, and H2O in the gas phase. This is all H2O. It's undergoing a physical change. It's going from solid to liquid to gas, but it's not changing its composition. In all three phases, it's still H2O. Okay? But the temperatures that these transitions happen are all influenced by the intermolecular attractive forces. Okay, so let's now delve a little bit deeper into this and start talking about them. And I'm going to start with the weakest forces. Actually, before we do that, let me remind you. The strongest forces are the intramolecular. Those are the bonds, the ionic bonds and the covalent bonds. When we're talking about the inter, right, they are weaker overall, but they also have relative strengths. Whoops. They also have relative strengths. I'm not going to hold you to, well, more or less. Let's just keep an eye on what the relative strengths are. The weakest ones are these London dispersion forces. They're named after Fritz London. Not that this is a history class, but I like putting names and dates on things just to give you a perspective. And this was, around 1928. So really not that long ago. Only a little less than a century ago. And this is describing a very, very weak intermolecular attractive force. And by the way, I'm going to use IMF for intermolecular force, intermolecular attractive force, just because it's a lot to write out each time, even though I may say it. Okay. This is a weak force that really exists on all molecules, even if they're nonpolar. And we'll show that in a moment. Even nonpolar molecules and even atoms will have these London dispersion forces. And to describe them a little better, let me first remind you of what a dipole moment is. A dipole moment is something that you described in lab, right? Monday, where it has two poles, right? It's a dipole. It has a negative end, a delta negative end, and a delta positive end. That little squiggle I drew, that's a lowercase delta, for those of you who don't remember, the Greek letter delta. And we use that for describing something that's partial. It's a partial plus charge or a partial minus charge. Now, if we have something like water, H2O, as you discovered, H2O has a permanent dipole across the entire molecule. We can describe that there's a little dipole. Why does it do that? We can describe that there's a polar bond here and a polar bond here, but overall, there's a permanent dipole across the entire molecule. H2O is a polar molecule. It's a permanent dipole. London dispersion forces are things that happen just for a moment, for an instant. They're instantaneous dipoles or temporary dipoles. They're not permanent. Instantaneous. Now, how do these arise? They arise due to a distortion of the electrons in the molecules or in the atoms. So I'm going to write that first, and then I'm going to talk about what that really means. Right? So these happen due to momentary distortions in the electron cloud. So what do I mean by that? Let me zoom in on one of these, just this one here on the left. Let's say this is just an atom. Let's say it's xenon. Okay? Here, let's put, here's the nucleus for xenon. How many protons are in the nucleus of xenon? Take a look at your periodic table. 54 protons. Now, how did he know that? Atomic number tells you the number of protons. That also means in a neutral, and it will be neutral, this is a noble gas, it's got its valence shell full. It's satisfied. It's not going to do any chemistry to gain or lose or share valence electrons because its valence shell is full. It's the stablest that it can be for that number of electrons. So the number of electrons then would be 54. So we've got 54 electrons somewhere in here, right? They're not in orbit. It's not the Rutherford model. We don't have, it's nice, right? Showing electrons in orbit around the nucleus. But we know from quantum theory that's not how electrons are organized in an atom. Instead, we have a probability area or volume where an electron might be found at any moment, but we can't really see where an electron is at any moment in time. That's the Heisenberg uncertainty principle. Anyway, here we have a nice distribution of electrons. We think of xenon, it's a noble gas. It doesn't do any chemistry with anything else. It's very stable. But these electrons don't all have to be evenly distributed. We don't know where they are. So it could be some moment in time here. Here, let's erase these. I know you're all going to say, oh, I just drew electrons all over the place. But let's say all the electrons in one particular moment in time just happen to be on one side for an instant, because the next instant they're going to be somewhere else. But for this one instant in time, we have all the negative charge is skewed to one side of the atom. And so here we have a dipole. We'll draw it this way. At this moment in time, we have a delta negative on the right-hand side and a delta positive on the left. This is what we call an instantaneous dipole moment. It's there one instant and it's gone in the next. So this momentary distortion in the electron cloud, this creates an instantaneous dipole. An instantaneous dipole moment. And then the next instant, poof, it's gone. But when it's there, you've got that dipole. If it happens to come close to another atom, let's just do another one here, and it was evenly distributed, but now it's coming close. So now this delta negative on this one, that's going to be a repulsive force against the electron cloud in the neighboring atom that it encounters. Okay, so we've got this momentary dipole, and it's going to then induce a small momentary dipole in the neighboring one because there's that repulsive force going on there. So now we've got this situation where we've induced another momentary or instantaneous dipole in the neighboring atom. And now look what we have. We have a negative next to a positive. What do we know about opposite charges? They attract each other. So that's going to create a very weak but a very real intermolecular attractive force. And then it's gone the next instant. Okay? So they're very weak, but they are measurable, and they do add up. So as things get larger and larger and more complicated, the more electrons you have to distort, the greater this effect is going to be. All right, so let's write this down as another bullet of what happens. So this instantaneous dipole moment can then induce the same in its neighbors. So this was a nonpolar atom or a nonpolar molecule. All right. But even in those cases, we can get small instantaneous polarity out of this that creates this London dispersion force. Sometimes they're just called London forces. Sometimes they're just called dispersion forces. All right. So when we have larger atoms or molecules, Oh, let's spell that cleaner. That's going to give us larger electron clouds. Which gives us more distortion. And with more distortion, we get stronger dipoles. But remember, these dipoles, these are instantaneous dipoles. Okay? So overall, we have a new word that describes this phenomenon. It's called polarizability. So depending on how you like to study, if you like to study definitions and stuff like that, maybe using a set of flashcards or keep a list. This is a new word. You should know what the meaning of this is, polarizability. It's a loaded word, and it means a lot. The more polarizable something is, you need to know what that means, right? It has to do with the ability to distort that electron cloud, and what are the implications? What are the ramifications of being able to distort that electron cloud? What relative effect is that going to have on the intermolecular attractive force? Now, I'll also mention these dipoles here, these permanent dipoles, that we draw this way. I'm just talking about them in a relative way. Relative magnitudes. We're not putting any hard numbers. We're not doing any number crunching in this first chapter for you. Although I will tell you that you can measure the magnitude of these dipoles. The units of this are coulomb meters, otherwise called a debye or debye. I'm not actually sure how it's pronounced. I'll put a capital D, that's the unit for it. So you may find, as you read through the chapter, that sometimes they'll give you an actual value of the dipole moment. That's okay. We're not going to be doing that. Right? You should recognize what it is, but if you're given that information, right, it's to be able to assess, well, what's going to be the relative intermolecular attractive force on, say, maybe compound A versus compound B versus compound C. And we'll have lots of chance to practice that near the end of this chapter together. But I'm going to put that in parentheses because really this is something that we're not going to be, well, you can't see that. We're not going to be doing this quantitatively. We're going to be working qualitatively. Here, let me just shrink this down. So it's not that important. It's just in parentheses. All right, so let's take a look at some examples here now. Let's look at a series of noble gases. These are atoms that are full valence shells. They're in group 8 of the periodic table. We start with helium, and then that's followed by neon, and followed by argon, and then krypton, xenon, and radon. Good, that all fits on there. And let's take a look at the boiling point. Now, we all kind of know what boiling point is. What do you think boiling point is? Who wants to define boiling point? Go for it. The point where it changes from a liquid to a gas. And that's a pretty good definition of boiling point. As you'll discover later on, it also is completely dependent on the pressure and the temperature. All right? So I will just qualify, it's not just the temperature that something goes from a liquid to a gas, but it is at a particular pressure as well. But we can use this as a measure, a relative measure of the intermolecular attractive forces. The stronger the attraction is between these atoms, the more energy it's going to take to overcome that attractive intermolecular force to get things to go from the liquid to the gas phase. But, I mean, these are already gases. You know these as noble gases. But if you get things cold enough, yeah, they'll go liquid. Absolutely, they will. So I'm going to put this in absolute temperature, so in Kelvin. And if you take a look, right, for Kelvin, helium has a boiling point of 4 Kelvin. That's pretty low. And if you remember the Kelvin scale, that's the absolute temperature. It's measuring the absolute kinetic energy of molecules. So you can't get any lower than absolute zero, which is no molecular motion, no kinetic energy. So helium is just above that for the boiling point. So you got to get it pretty darn cold to get helium to go liquid. But if you look at this trend, neon has a boiling point of 27 Kelvin, argon 87 Kelvin, krypton 120 Kelvin, xenon 165 Kelvin, and radon is 211 Kelvin. So Kelvin is the degrees Celsius plus 273. So if we look at the freezing point or melting point of H2O, that's going to be the temperature where H2O goes from the liquid from the solid to the liquid phase. What temperature under normal 1 atmosphere pressure, what temperature is the melting point of H2O? It's 0. So H2O, the freezing point or melting point is 0 degrees Celsius. So that's what in Kelvin? 273. So radon then, the boiling point of radon is still relatively high, okay, but it's still lower than the melting point for H2O. So yeah, these are typically gases under standard temperatures and pressures. But what you can see here is the trend in increase in boiling point, and that's all due to these London dispersion forces. There's nothing else going on here. The larger the atom is, the more electrons there are, the more distortable they are, so the polarizability is greater as you increase in size. All right? That's the main point there. So let's take a look at a couple of examples then from the textbook. These are all figures and tables taken from your textbook. Let's start with the lower left here. Okay, this is showing you the same trend as I just did with the noble gases, except now we're looking at the halogens. So this is the same trend as in the noble gases. Except now we're dealing with the halogens. These are elements that are in group 7. And notice that they're all diatomic molecules. Why is it that they're diatomic molecules and not single atoms? Who knows? They only exist in nature as diatomic molecules. That's true. Why is that? Right, so they each need one more electron to become the most stable that they can be, fill their valence shell, and they each also have an unpaired electron that they can donate to the other one. So together they'll form a covalent bond, and in nature that's how you find these most stably. There's a few others, right? Hydrogen and nitrogen and oxygen will also do this. They'll form diatomic molecules. And those of you who had me for Gen Chem 1 know how to remember that, right? Who wants to sing it?
I can't remember it.
Okay, so it goes like this. All of the elements that end have a suffix that either ends in GEN, so like oxygen, hydrogen, nitrogen, or if it ends in INE, right? Iodine, fluorine, fluorine, chlorine, right? All of these end in either INE or GEN. They will be the most stable in nature when they combine diatomically. Now, do you remember the song? GEN and INE are found in nature diatomically. Ta-da. Come on, you guys sing it. GEN and INE. Oh, come on, that was pathetic. Here, I'm going to put the microphone on here. One more time. Key change. GEN and INE. All right. Now you'll never forget it. Of course, you can also just look on the periodic table, and if you know your way around, you can remember that just as fine. But that's why these are diatomic. But the trend here is the same. All right. As we increase in size, we're increasing the polarizability of the electron cloud, so there's greater London dispersion forces. Upper right. Here we have a series. We learned this word on Monday. These are all hydrocarbons. These are molecules that only contain carbon and hydrogen. And Actually, both of these panels are hydrocarbons. And we see two kinds of trends here. But first, let's take a look at the axes. Here we have the overall molar mass. This is in grams per mole. And on the left axis, on the y-axis, we have the boiling point. And you can see that there's a general trend as we're growing the hydrocarbon chain, we are increasing the boiling point. So we're doing two things here. We're increasing the mass, or we're increasing the size. Well, let's just say increasing the mass. That's fine. But we're also making it linear. We're extending it into a linear chain. Both of these have an effect. Now, increasing mass, I don't need to explain that one to you again. But the more linear, that's something that's more easily shown here when we're looking at these three structural isomers. So we learned that on Monday as well. Structural isomers. All three of these things here, and here they're even named for you: pentane, 2-methylbutane, and 2,2-dimethylpropane. These are all the same molecular formula, which is C5H12. Now, these names here, pentane, 2-methylbutane, 2,2-dimethylbutane, 2,2-dimethylpropane, you'll learn about how those are named when you take organic chemistry. So that's what's in store for you there. But take a look at the boiling point. And again, this is in Kelvin. And we see that here we have 309 Kelvin for pentane, 301 Kelvin for 2-methylbutane, and 282 Kelvin for 2,2-dimethylpropane. It's getting lower. And what's happening here? It's the same mass, but the linearity is changing. As we get more compact, as we get more dense, or in this case, more branching, what we're doing two things to the polarizability. We're basically decreasing the overall surface area for where that polarizability can take place. And let's put this in a new, just to highlight these things. With this, we have decreased volume for polarizability, and we also then have, along the linear dimension, we have more points of contact between the molecules. Okay, so basically the polarizability gets greater as we go from right to left. All right? Because we're extending, as we get more linear, we get more polarizability because the volume is increasing of where that distortion can take place over that distance. And then if you look at the dotted line there connecting the two, we have more points of contact along the surface area of both molecules for them to interact more. So it's subtle, but you can see that then in the small change in boiling points. And we would see similar trends if we were following freezing points or if we were following vapor pressure, which you haven't learned about yet, so don't worry, that's coming up. Or viscosity, which we'll probably talk about at the end of this chapter. All right, all of these things are dictated by these intermolecular attractive forces. And again, this is still just London dispersion forces that we're talking about here. Okay, so now let's move on to a little bit stronger intermolecular attractive force. And these are going to be involving dipoles, but now we're just having dipoles between a molecule that's polar and a molecule that's nonpolar. So if we have a dipole, that would be a polar molecule. And if we have an induced dipole, well, that's what I just told you about. The induced dipole, that's what happens instantaneously when a nonpolar thing, a nonpolar compound, is next to something that has a small dipole. So this would normally be nonpolar. And a perfect example is molecular oxygen dissolving in water. And thank goodness for the fishes that this happens, all right? Because the fishes, right, and sea mammals, well, the fishes, let's say, they need oxygen just like we do, but they get it from the water. So O2 has to somehow dissolve in H2O. But how can that happen? O2 is nonpolar, right? If you take a look at O2, we have a bond here, but the electronegativity on both sides of that bond is the same. It's oxygen on one side and it's oxygen on the other side. So there's an equal sharing of electrons, right? The delta electronegativity is 0. So it's normally nonpolar. But as we just learned, we can distort that a little bit if we put it next to something that has a dipole moment. And water certainly does. I already drew water for you earlier, so I'll just remind you that overall in water, there is a net dipole moment. Remember, there's two polar bonds, but they don't cancel each other out because the geometry is bent. So that creates an overall permanent dipole moment. That's going to give us a delta negative and a delta positive. And when that happens, we're going to induce a dipole moment in the O2. Okay? It's not that much of a leap of a concept based on the discussion that we've been having so far. So this effect allows for nonpolar solutes to dissolve in polar solvents. Now there you got to remember a couple of words, like solutes and solvents, which you should have learned about in Gen Chem 1. So I'm not going to spend the time to quiz you to remind you of what they are, but I'm going to highlight them. You should know the difference between a solute and a solvent. When we're talking about polar and nonpolar, normally they don't go together. We say that opposites attract when we're talking about charges, but what do you know about polar and nonpolar? Do they like to mix together or not? They don't. Who likes Italian salad dressing? I sure do. You guys don't like Italian salad dressing? It's basically oil and vinegar. Now, what's vinegar? Who remembers what vinegar is? In water. Very good. Acetic acid. Vinegar is a 5% solution, so acetic acid is the solute. Actually, let's put this down. That's a great example. Vinegar is a 5% solution of acetic acid in water. Water is the solvent. Acetic acid is the solute. Now, in this case, acetic acid is also polar, and it's got some other things going on as well. Okay, but it is an example of solutes and solvents. But when we mix that with oil, so vinegar is very polar. Oil is very nonpolar. So that's why when you don't mix up your Italian salad dressing, the two phases separate. The two liquid phases will separate. They don't want to mix. When they do mix, so when liquids mix completely, and that's regardless of the ratio. So in any ratio of one liquid to another, there's a special word for that. When they do mix completely, that's called being miscible. Here's another word for you to know about. And again, all of these words, these definitions, you can look these up in the chapter as well. So that's when liquids mix together. Now here we're not talking about one liquid and another with oxygen in water. There we're talking about a non-liquid dissolving in a liquid. So that's similar. In this case, what we have is solubility. This is now where we have a gas in water. It's still a solid and a solvent. But now in this case, the gas is a non-polar solute dissolving in a polar solvent. So whereas in miscibility, they mix 100% regardless of the ratio, with solubility, there is a point at which you saturate the solution. And once you've saturated the solution, you can't get any more solubilized. Right? So this is limited by saturation. That point beyond which you cannot get any more of the solute solubilized in the solvent. And for most materials, you can look up what the value is for how much can you get solubilized in the solvent before it becomes saturated. And in the case of oxygen, we can actually measure that. Now, of course, this is also going to be dependent on the pressure and the temperature, okay? But under standard conditions, we can write down what the saturation is for O2 in water. For O2, you can get 1.3 times 10 to the minus fourth moles of O2 dissolved for every liter of H2O per atmosphere of pressure. That's a hard number. And in fact, we can factor in, well, what is the atmospheric pressure of O2? All right? And we can, of course, control the volume of water. So factoring in pressure and factoring in the volume, we can actually calculate how many moles of O2 can you get solubilized in H2O. And we will be doing that, but not today, and not in this chapter, because we're not going to be doing any hard computations in this chapter. But just to make this point, all right, let's look at carbon dioxide. For those of you like me who enjoy your frosty carbonated beverage in the afternoon, right? That's carbon dioxide solubilized in water. It's the same principle, the same ideas, and the same factors on this. So we have another value that we can write down. Under standard conditions, we can get 3.4 times 10 to the minus second moles of carbon dioxide solubilized for every liter for every atmosphere. All right? Just to foreshadow, all right, this is all Henry's law. And that's coming soon to a lecture near you. All right? But in the context of today's discussion, though, take a look at this. They're both, let's see, we already know oxygen is nonpolar. Is carbon dioxide polar or nonpolar? It's also nonpolar. So these are both nonpolar solutes being solubilized in a polar solvent. Which one, for every liter and for every atmosphere, which one can we get more into the solution? O2 or CO2? Let's just see a show of hands. Under the same conditions, who thinks that we'll get more oxygen dissolved? Who thinks we'll get more carbon dioxide dissolved? Right, very good. Right, that's what this number is showing you. We can get more moles of carbon dioxide dissolved per liter per atmosphere than we can of O2. Why? 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 What's going on? What's different about CO2 and O2 that would explain why we can get more carbon dioxide dissolved in water? Give it a shot. CO2 is larger. You've got one carbon and two oxygens, whereas in molecular oxygen, all you have is two oxygens. So CO2 is larger, So it also has a greater mass. That's kind of what I mean by larger. It has more electrons. It has more surface area. It overall has more polarizability. Meaning that for London dispersion forces, or for it to be able to have a induced dipole, same principle, okay, you can induce a stronger dipole. Again, we're not putting numbers to this. But if we just looked at the dipole that can be induced, how polarizable is O2, the electrons in O2? How polarizable are the electrons in CO2? You can see that you can induce a stronger dipole in CO2. Therefore, it's going to be more like the polar solvent than O2 will be, which means you can get more of it dissolved. All right? So hopefully it's starting to make more sense. Okay, so now let's talk about even stronger than dipole-induced dipole are good old-fashioned dipole-dipole interactions. This is where you have an interaction between two substances and both of them are polar, which means they both have permanent dipoles. So we don't need to spend a lot of time discussing this. I think you're going to get the idea pretty quickly. Now we have permanent dipoles, and I can draw them across all of these. On the left, we have methylpropane, and you can see what the boiling point is there, again in Kelvin. And on the right, we have 2-propanone, otherwise known as acetone, on the right. Now, the book likes using this color scheme to show you the relative strength of the dipoles, where red is very, very strong, and I think green is neutral, and there's a color scale there. That doesn't matter so much, and in fact, I probably would have chosen a different molecule to work with on the left, because by color scheme, it doesn't really look too much like it's polar. But you can tell, if you look at the Lewis structure down below, that it is polar, because this is tetrahedral, and we can see that we've got different dipole moments on the 4 bonds. One of them is different. So the carbons are a little bit more electronegative than the hydrogens are, and you don't even need to know that. All you need to recognize is that if it's tetrahedral, you know that they're in opposition, but the magnitude of the dipoles are different. And if they're different, you're going to have overall a permanent dipole moment. I might draw it across the molecule like this. Delta negative on this side, delta positive on this side. For acetone, that's pretty clear. The oxygens are very electronegative, so we're going to be delta negative here, delta positive here across that molecule. And these are permanent. Both are permanent dipole moments, so they never go away. So that's obviously going to be stronger than any kind of an instantaneous dipole, which by its name implies it's sometimes there and it's sometimes not there. Okay? So we don't really need to spend much more time on that type of interaction. So actually, before I talk about hydrogen bonding, which is the next strongest strength-wise for your intermolecular attractive forces, and I'm sure you've all heard about hydrogen bonding, especially you biology majors out there. How many biology majors are there? Nice and high. Not that many. How about biochemistry? Okay, more biochemistry. So still, I think we've all heard of hydrogen bonding before. And really, hydrogen bonds are not much different from dipole moments. In fact, they are dipole moments. They're just the strongest dipole moments that we have. And let me discuss that a little bit. So once again, if we think about our bonding situation, if we have two things in a bond and the difference in electronegativity is 0, then we know for sure that's a non-polar covalent bond. That's what we would call that. And that's what you have with those 7 elements that form molecules in nature, G, E, N, and I, and E. All right? Those will all have the Completely non-polar covalent bonds. There's no difference in electronegativity there. Just a little bit of London dispersion forces. But then when we get differences in electronegativity, we end up with our polar bonds. That gives you a dipole moment. All right, so this is what we would have for a polar covalent bond. And then at some magic point, the difference in electronegativity is so great that it's no longer a dipole. You're not unevenly sharing electrons. In fact, one has lost an electron or two, and the other one has gained an electron or two or three, depending on what it is. When the difference in electronegativity is so great, you end up with cations and anions, but they are still attracted to each other due to the positive and negative charge of the ions now. This is what then comes together to form the ionic bond. And there's no magic place where all of a sudden it turns from being polar covalent to ionic. Although the textbooks might lead you to believe that there is a magic number. That's why I never teach the delta En of like 1.8 or 2 is the magic point between where it goes from polar to ionic. It's really a relative scale. And when you get to that gray area, we actually describe these bonds as being like 60% covalent character and 40% ionic character and whatnot. It's really not black and white in that sense. So all hydrogen bonds are the most polar covalent bonds that we have before they become ionic. Before we actually characterize them as being ionic, before being ionic. And we only see this, these strongest ones, when hydrogen is bonded to three elements, the most electronegative elements that we have, which are fluorine, nitrogen, and oxygen. But it's not just that they're the most electronegative, it's also that they're small. All right. Now, I don't have time to explain to you why that is, so that's where we're going to pick up in lecture on Friday.